Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to Instrumentation and Measurement. This is lecture number 6. Today we will explore about the experiment of of a sensor or a system, the data generated from it, and then use of regression analysis in the instrumentation and measurement systems. Having a generalized model of a system or element, uh, we have seen that the system can be represented by a mathematical model in which we have non-linearity, the linear model, and the environmental effects like the modifying input and the interfering input. But practically, what is the non-linearity, the sensitivity constant, the sensitivity of from the modifying input, from the interfering input, and what is the dynamic system model of this element. So this is a big question, having a sensor or a system in hand. So for to calibrate or to find the internal components, the first thing we need to do is like we conduct some kind of a experiment, or like we do in the calibration. This will is done by providing some input data and getting some output data, and then having the data, we analyze the input output data with the questions, and we try to find out the individual elements of this, for example, this mathematical model. So this is the a kind of a data analysis, or for instrumentation that we are going to study. So there are three parts of a calibration experiment: the output versus the input, while keeping the modifying input and the interfering input at constant, like as at the standard uh, temperature and humidity. And second is the output versus the IM and II, the interfering input and modifying input, while we keep the main input constant. And then the third is the repeatability test. So calibration experiment 1, it should be at the standard environment conditions when the IM and II are 0. If not, then all the environmental inputs should be measured. If we are unable to keep them at the constant value, then we should have some sensor that if for example modifying input and interfering input are like ambient temperature, or the pressure or humidity, so we should have a sensor that is recording this that data as well. So how we do it? Calibration: increase the input slowly for from Imin to Imax, and record the values for the input and output and intervals, for example at 10%, and then we will have around 10 readings. Then no we have to allow sufficient time to settle down for the output before we should record the saving, we should record the values. Then decrease the I slowly for the Imax to Imin, so coming back, and record another set of the 11 readings. Repeat 2 or 3 times up and down the whole experiment. So we will have different sets of the input and output data pair while the input is increasing, and we will have different data sets of input and output depending upon when the input is decreasing. So for example, the subscript I and j from 1 2 3 up to n, and maybe like for example 33 readings. Ultimately we will have a total of 33 readings. Now, having the data, what we do is we can use the computer softwares, for example some kind of regression packages in MATLAB or some other softwares. Every other software has the simple regression packages. In regression package, what we do is we fit a polynomial, for example the output equation as a polynomial function of the input, so to a data set, and we use these data sets to try to fit on it. Fitting means we are trying to find the appropriate coefficients for this polynomial. So these packages use mainly least squares criteria, in that if di is the division of the polynomial value from the data value. This the difference between this polynomial value minus the data value. So note that this oi is the actual value, and this II is basically the polynomial value, and di is the difference between this data point. So the computer program will find a set of coefficients a0, a1 and a2, etc., such that the sum of the squares of the deviation, for example, this error di square from I for all the data points from I1 to In is minimized. So this is basically involves solving a set of linear equations. This is from linear algebra. For example, now if we are looking to find the hysteresis of this element, whatever we have, we perform separate regressions on the two data sets. We have one data set while the input was increasing, we have another data set while the input was decreasing, and this will give us the two polynomials individually. One was for the while the input was increasing, the other will be the decreasing. And the polynomials, if, for example, if you draw, it will be just like on a graph. It will be if we see so that it will be like so the one polynomial will be maybe, for example, like this, and the other polynomial will be like coming back like this. Okay, so we will have two different polynomials, one for increasing, one for decreasing. If the hysteresis is significant, then the separation of these two curves will be greater than the scatter of the data points. So you can see, if we can assume that we have the data point, like let's say some data points like here, data points some here, some data points here, some data points like here. Okay, so this will be of course the data points used for. Okay, so if this is if hysteresis is significant, then the separation of the two curves will be greater than the scatter of the data points about each individual curve. Okay, and this is how we will calculate. We subtract these two and we will have the hysteresis equation. Temperature sensor, for example, are often calibrated using the appropriate fixed points rather than a standard instrument. For example, a thermocouple may be calibrated between 0 and 500 degrees by measuring EMFs at, for example, ice, steam, or zinc points. So if EMF temperature relationship is E equals to A1T plus A2T square plus A3T cube, then the coefficients can be found by solving the three simultaneous equations at these points. This is also in the end one problem to problem 21, problem 2.1 in Bentley 4th edition. Okay, and we will do it in another video. Now, having the data and the basics of the regression, now we will go through the regression analysis. Regression analysis is a very useful tool in the field of instrumentation and controls. This can be used to obtain working models from experimental data as well as real-time data. The experiment data is basically the data you generate and then you do some offline analysis and do it. Real-time data is like, for example, you have a continuously plant is running and you have continuously getting some data from the instrument, and you do a real-time analysis of knowing about, like, for example, the continuous drift or some other nonlinearity, and then it is being used in providing and developing some advanced algorithms like model predictive control or advanced process controls. Coming back to this point, that this is usually and this is also regression analysis is the first technique taught in the data science and system identification professionals, which is very it's applied and an essential tool in current field of instrumentation and controls, where we have the DCS and advanced processes and a lot of data from the industry. In instrumentation and measurement course, here, for example, we first use the regression analysis to the problem of finding the static model for a sensor using the calibration data. So this will be our first task as a data analyst or data scientist in this field of instrumentation measurement. This will be the first task for him her that they use the calibration data to find the static model of a sensor. Now, the regression analysis is basically a statistical analysis in which a mathematical model is fitted on a given data set. So, fitting a mathematical model means finding the unknown model parameters. Now, assume this is an example in which we have, let's say, we have a sensor, and the calibration data of the sensor is we provide some force, and then the sensor was able to give us some voltage output. So the one input was 1 units, the output was around 2 units. It may be millivolts or volts, we are not bothering about the units, but this 1 units for the force input and 2 units was the output voltage. Then 2.3 units for the force input and 4.4 units for the output voltage, and similarly these data points. So the first step as a data scientist or analysis is we should visualize our data. So just plot the data, and we have some sort of the values like this, just the data points. Now the regression starts. We need to fit a linear equation model, because it looks like that, okay, a linear equation will be sufficient for this kind of data. A linear model to give the data means a linear model will be y equals to k x plus a. Why we are using subscript I? Because we have around 1 2 3 4 5 pairs, 5 data points. So y1 equals to k x1 plus a, y2 plus is equals to k x2 plus a, and so on. So for all the data points, this model should be should be satisfied, where xi and yi is the given data set, and k and a will be the best fits. Now we can see that the line may not be passing through all of it, so we have to find a best k and a that will make sure that, okay, maximum number of points are passing through this line. So fitting a quadratic model, in case of if we are looking for to fit the quadratic model, the quadratic model will be like this: yi equals to a naught plus a1 xi plus a2 xi square. Notice that we have now 3 parameters: a naught, a1 and a2, and we are using and we will be using the same data points, but this time this will have a curvature and more than an inline. Okay, it might be possible that less number of data points will be passing through the line. In quadratic model, we can make sure more data points will be passing through this one. So this is all. We have the given set, and we have the option of fitting the best possible model. Now, how to find the k and a? The formula for finding the k and a is derived from the optimization theory. Now we are going to we are not going to write some algorithm right now. We are going to find an equation that will use the data, and it will give us one quick answer, the best answer. Okay, so one best answer for k and one best answer for the a, and it is derived from the theory, optimization theory. The method used from optimization theory to derive the equations for k and a is called basically least squares estimate, and next we will use the least squares method to find the equations of the best k and a. So case number 1, for example, let's assume that we want to fit this linear model. So finding a linear model using the regression analysis, let yi represents the data points, and I will be equals to from 1 to n, so we have n data points, and yi hat is the model prediction. So this is not yi hat is not the actual data, it is the data which is we calculate from this linear equation. Note that in this equation you just place the real data value for the xi, a value for k and a, and then whatever we are getting from this one is the data from this model. So this is the predicted, and note that we already have yi without hat. Our job is to find the best k and a. So step 1 will be find equation of error. So error means the one we calculated from the model, predicted model, and one y we already have from the real data. So this is the real data yi, and this is the yi from the model, mathematical model. This is called the residual. So the residual is error, or residual is x is the epsilon I equals to yi plus minus yi hat. Step 2 is use a method from the optimization theory to find the best values of k and a. A well accepted method we just discussed for to minimize is the sum of the squares of error, least squares method, in which what we do is we form this object, this cost function, or and try to reduce this. So the cost function by x, this is epsilon, epsilon e, the epsilon I is the difference between yi minus yi hat, and notice that yi hat is basically k xi plus a. So yi minus a minus k xi, we replace the value of this is the value, this is the whole value is from this one, okay, yi hat. Okay, so yi hat is basically this whole value, and we place k xi plus a here, and so this value will help us, so this will be our cost function, and we have to minimize this error by changing different values and for k and y. So we minimize e and try to find the values of k and a which help us to achieve the minimum of this is also called cost and j object function. Now to find the maximum, now to find the minimum of the j cost with respect to the k and a, we only need to differentiate and equate to 0. So this is how we will do the function j is differentiated with respect to one of the parameters, which is k, equate it to 0, and here it is, we place this value j is here, differentiate. So when you differentiate this value, this will be 2, okay, this whole will be 2 summation, and this whole value, and then differentiate it second time because we still have some k here. We solve it, and finally we have 0 minus xi, then multiply, take the 2 on the other side, rearrange, and finally rearrange in a manner so that your unknown parameters like a and k terms are on the left side and the rest will go on the right side. Notice that this yi and xi are all the data points, and we can easily calculate. This is not unknown. Here the unknown is k and unknown is a. This summation xi can be calculated because we have all the n data points. This xi square, summation of xi square can be calculated because we have all the data points, and similarly yi and the product of this summation will be also be calculated because we have all the data points. Now we go for the second parameter, differentiate j with respect to a, the second parameter, with and we differentiate and equate to 0 to find the minimum. Solve it like this, and finally you will arrive to equation number 2, and a plus k summation xi, and the summation of yi is here. So this now equation number 1, this equation, and equation number 2, these are also called the normal equations or the regression equations. Now these equations, since we have notice that we have a, first term is a times this plus k times this equals to this, and then we have a times n plus k times this equals to this value. So we can write them in the matrix form. Equation 1 and 2 can be rewritten as this, and then we have the one matrix times this vector equals to another matrix. So let's call them, you see this is another matrix, so I better, and this is one parameter vector, and this is like a data vector, so I better call them the data matrix, parameter matrix, vector, and the output matrix. Okay, so I call them d dot p equals to 0, and if you and then the d, taking d matrix on the other side, we have to take the inverse, and this is the value of d, d11, d12, d21, d22, and d11 is basically n, d12 is summation of xi, d21 is summation of xi, and d22 is summation of xi square. Asymmetric matrix, because you see the elements on the off diagonal elements are same, summation xi and summation xi. Notice that I'm just writing summation. Basically this is x summation from I equals to 1 to n, and the output matrix or the vector is O11, O21 is summation of yi and summation of yi times xi. Coming back to the example, so this was the example for force and sensor. So summation xi can be calculated by using this xi. So I add 1 plus 2.3 plus 2.9 plus 4 plus 4.9, we will get this some 15.1. Similarly, summation of yi for n is 5 here and equals to 5 here, so 2 plus 4.4 plus 5.4 plus 7.5 plus 9.1. make sure that, okay, please check it and let me know if any the values are correct. So this will be 28.4. now for xi square, okay, this first I calculate here this xi1, this square is 1 square is here, 2.3 square is 5.29, 2.9 square is 8.41, 4 square is 16, 4.9 square is 24.0. and now once you have all xi squares like this, you sum them up, 1 plus 5.29 plus 8.41 plus 16 plus 2.4.24.01, so it will be 54.71. and then we have another calculation here. You see this summation of xi and yi. So we what we do is, this is xi, this is yi, multiply them, 2 into 1 equals to 2 here. Then 4.4 is yi, 2.3 is this, so 2.3 times 4.4 is 10.12. Similarly, 2.9 times 5.4 is 15.66. 4 multiplied by 7.5 is 30. 4.9 into 9.1 is 44.59. and once we have all of these, this is the y1 x1, this is y2 x2, this is y3 x3, y4 x4, and then y5 x5. now this yi xi summation applies to them, so you add 2 plus 10.12 plus 15.66 plus 30 plus 44.59, and we get 102.37. so now we have calculated these four terms. And notice that this is we have to put n here to calculate the summation xi and summation xi square. If you notice, we have the summation xi 15.1, so 15.1 comes here and here, n equals to 5 comes here, and then we have this summation xi square is 54.71. and then we find the inverse of it, as because this the parameter vector is equals to d data matrix inverse times the output matrix or the vector. So we calculate the inverse adjoint of a divided by the mod of a. This will be a little matrix, and then we have the output. If we see the output is summation yi and summation yi xi. Summation yi is 28.4. We calculated from here, 28.4 here, and 102.37 from here. So we keep them here and multiply this with the inverse of this matrix. We will arrive to a will be 0.1752 and k is 1.828. So these two are the best from these data points. You notice that individual the two data points can be used to find k and a, any of the 2 points, but to make sure that we have the best line for this one is this method of least squares. And so we have the identified model utilizing all the 5 data points, and even 100 of data points we can use is this method. Y hat equals to 1.8228 xi plus 0.1752. Now case 2 is can be the fitting quadratic model on the data. So the first step is to find the regression or normal equations for the parametric model. This is the model, mathematical model, and for the least squares estimate, what we need to do is this error, this cost function, we have to minimize. Now this time we have to minimize it with respect to the parameters. Last time they were k and a. This time we have a0, a1 and a2. So we have to we have to minimize the cost by finding the best values for a0, a1 and a2. So yi is the data point minus, this is the from the predicted model. Replace this whole predicted model here, this whole predicted model. Okay, we bring it here, and from yi hat. So yi hat we place it here, Okay, so we get this value, this equation of the cost function j, and then the next thing we need to do is we need to differentiate it with respect to every parameter and equate to 0. So first we differentiate with respect to a naught, equate to 0, and arrive to one equation, and arrange them, because we need to write them in a proper matrix form. So arrange them in so that on the left side you have a proper sequence arrangement of the unknown variables, and on the right side the whatever we can we have the as a data or available value. So n a naught plus summation xi a1 plus summation xi square a2 equals summation yi. Differentiate with respect to a1, we arrive to this equation, a naught times this, a1 times this, a2 times this, and on the other side we have summation xi yi. Differentiate with respect to a2, the same cost function, we will arrive to this third equation. So having these three equations, we have these like a normal equations. For the quadratic model, this time the normal equations are different every time, because model changes, the equations will be a little different. So rearrange them into a proper matrix form. We have like this is the whole data matrix, this is the parametric or unknown parameter vector, and this is the vector for the output. I call it the output data, because you see all the outputs are there, although the input is also being multiplied here. So but I better call them, this is the output matrix or vector, this is the parametric vector, and this is the data matrix. So the data matrix dp equals to 0 and p equals to d inverse o. So this can be used to find the quadratic model of the previous sensor, and this is your homework assignment. Try to do this by calculating for the same assignment from the same data. Use the same data set, but this time try to find use this one to find the parameters of a naught, a1 and a2. So for the same sensor you will be able to find the quadratic model of the sensor. Thank you very much. For any questions, queries, please write me through to via this emails. Thank you very much.